Hello dear classmates, welcome back to the memory testing chapter. In this video, we are going to introduce a very important memory testing technique, the March algorithm. We will introduce many algorithms in this March test family according to their history. First of all, a March test algorithm has a sequence of March elements, and in each March element we have two important information. One is the operation and the data. For example, R0 means that we are reading an expected 0 from the memory cell. R1 means that we are reading an expected 1 from the cell. W0 means that we write a 0 to a cell, and W1 means that we write a 1 to a cell. And the second, in a March element, we also specify the address sequence. An upward symbol represents the address are changed in ascending order, and the downward arrow indicates that the address are changed in descending order. A double arrow means that the address sequence can be either ascending or descending. For example, this is a simple March test algorithm. This test algorithm has 3 March elements. Each of them are separated by a semicolon symbol. The complexity of this March element is 4n because we have 2 write and 2 read for each cell. So, in summary, March test is a very good, efficient test for memory that can be done in linear time. Now it's a short quiz for you. Given this March test, please tell me how many March elements are there and what's the time complexity. Okay, are you finished? We have 1, 2, 3, 4, 5, 6, 7 March elements. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the time complexity is 11n. Is it very simple? Okay, now let's introduce the first March test algorithm, the MemTest algorithm, proposed in 1979. The full name is Modified Algorithmic Test Sequence, or MemTest. The MemTest algorithm contains 3 March elements. In the first March element, we write 0 to all the cells. It can be either ascending or descending address order. In the second March element, we read a 0 and then immediately write a 1 to the same cell. And then we increase the address. After we go through all the memory cells, then in the third March element, we read 1 to a cell and we decrease the address in descending address order. So this March test can be illustrated in this figure. After we have written 0 to all the cells, now the memory is like this. And then we start the second March algorithm. We read a 0 and then we write a 1 to address A1. And then we read 0, write 1 to A2 and A3. In this way, we finish the second March element. In the third March element, we read the 1 from A3 and then A2 followed by A1. In this way, we finish all the math tests. The math algorithm detects all the single stacks 4. It's obvious because we read 0 and we also read 1 from all the cells. However, it only detects half of the transition fault because we have only 0 to 1 transition, but we don't have 1 to 0 transition. So that's why we detect only half of the transition fault. The complexity is 4n. So how about address decoder fault? Continue from that page. We have this math algorithm. Suppose we have an OR type address decoder fault between A3 and A1. Now, suppose we are in the second March algorithm, R0, W1. So we have finished the other two cells. Now we are trying to read a 0 from A3, but there is address decoder fault. So we access A1 at the same time. When we read A3, we can detect the OR type address decoder fault. Good value is 0 and the faulty value is 1. However, we cannot detect the N-type address decoder fault. So what should we do? A very simple idea is that we can just reverse the math algorithm. So we reverse all the 0 and the 1 from the original math algorithm. In this way, we can detect all the N-type address decoder fault. However, now we cannot detect the OR-type address decoder fault. So, in summary, the original math algorithm detects all the StarCat 4, but it only detects half of the address decoder fault, and the complexity is 4n. Now, if we want to detect both address decoder fault, what should we do? In 1983, MATS Plus was proposed that combines both N-type and the OR-type MATS. It's very smart that we only need to add one W0 at the end of the last March algorithm. In this figure, now suppose that we finish writing 0 to A3 and we also write A2 to 0. Now, when we want to read a 1 from A1, we also access A3. At this time, we can detect the N-type address decoder fault. So the MATS Plus algorithm only increase the complexity from 4n to 5n, but now we can detect both types of address decoder fault. This is a very smart idea. So, how about the transition fault? In 1991, Decoder proposed an even better math algorithm called MATS++. It was modified from the MATS Plus by adding one more read 0 to the end of the last March algorithm. This MATS++ algorithm also detects both transition delay fault. This is because we have a 0 to 1 transition and also we have a 1 to 0 transition. And we read a 0, so that we can detect the transition fault. The complexity is now increased a little bit to 6n, but we can detect all 3 fault models. This is a very smart idea. And how about coupling fault? Now it's time for you to work on this quiz. Given this MemTest algorithm, can we detect the inversion coupling fault? The inversion coupling fault means that when the aggressor is having a falling transition, the victim cell would be flipped. In this quiz, suppose that address A1 is the aggressor and the A3 is the victim. Now please fill in these question marks and answer this question. Now please pause your video. Okay, have you finished? In the first figure, suppose that we have finished writing 1 to all the cells. In the second figure, now we have a falling transition at A1, the aggressor. At this time, the victim would be flipped and complemented. But at this time, we already finished the MemTest algorithm, so the fault is not detected. So the answer is no. MemTest cannot detect the inversion coupling fault. Have you got it correctly? Okay, now that we know the problem is in the last operation, can we modify the MemTest algorithm to detect the coupling fault? It turns out to be very easy. The March X algorithm simply modified the last operation. It has a separate March element to read the 0 such that we can detect the fault. Let's consider the same example. Consider the inversion coupling fault between A1 and A3. At the end of this operation, we activate the fault at A3. And then, at this time, the March X algorithm proposes an independent March element to read a 0 from the memory. In this way, we can detect the fault at the victim. So now, the March X algorithm is able to detect the inversion coupling fault. It's a very smart idea because this is just a small change to the original algorithm. But remember, there are still other inversion coupling faults. Let's consider all 4 types of inversion coupling faults. Case 1 and case 2 are the same type of inversion coupling fault. When the aggressor is having a rising transition and the victim is complemented. Case 1 and case 2 are different in the position of aggressor and victims. In case 1, the aggressor is at button A1 and the victim is up here in A3. But in case 2, the aggressor is up here at A3 and the victim is down here in A1. The case 3 and the case 4 are similar to case 1 and case 2, but now the aggressor is having a falling transition. Okay, let's look at case 1 first. For case 1, we can activate the fall in the second March element, where we write the aggressor to 1, and this time the fall is activated. The fall activation is represented in green color. And then we access A2 followed by A3. At this time, when we read a 0 from A3, we detect the fall. The detection is represented in blue color. So for case 1, the detection is successful. For case 2, at the end of the second March element, we write the aggressor to 1, and at this time the victim is flipped to 0. But the fall is not detected by the second March algorithm. Actually, it will be detected in the third March algorithm. When we read a 1 from the A1, at this time we can detect the fall. And it can be seen the same thing happened to case 3 and the case 4. You are welcome to verify by yourself. In summary, we can detect all inversion coupling fall by March X, and the complexity is still 6n. Now, how about the other coupling faults? The March C algorithm proposed in 1982 combines two March algorithms together, but they are in opposite address order. As you can see, the first half of the March algorithm is very similar to the second half of the March algorithm. They are only different in the address order. Now let's consider the idempotent coupling fault. There are actually 8 cases, but now let's consider first 4 cases. In case 1 and the case 2, they are rising transition in the aggressor, and the victim is forced to 1, or the victim is forced to 0. In the third and the fourth cases, the aggressor is having a falling transition and the victim is forced to 0 or 1. Now, for case 1, when we write A1 to 1, the victim is forced to 1. It can be detected by the same March algorithm when we access A3. For case 2, we can see that in the second March element, A1 is written to 1. At this time, the victim is forced to 0. In the third March algorithm, when we read A3, we can detect the fall. For case 3 and case 4, they are very similar to case 1 and 2, but now they happen in the second half of the March C algorithm. There are still 4 other cases when A1 is victim and A3 is aggressor. The other 4 cases are symmetric to case 1 and the case 4. So you are welcome to perform the check by yourself. Now it's time for you to have a quiz. We already shown that March C detects inversion coupling fault and the idempotent coupling fault. How about the state coupling fault? In this quiz, please consider A1 is the aggressor and the A3 is the victim. For case 1, we consider that when an aggressor is 1, a victim is forced to 1. Case 2 means that when the aggressor is 1, the victim is forced to 0. And third case and the fourth case are similar. So now please pause the video and fill in the question marks. Okay, have you done? In the first case, when the aggressor is written to 1, the victim is forced to 1. This can be detected by the second March element. For the second case, same thing here. It can be activated by the second March element and it's detected in the third March element. Case 3 and the case 4 are similar, but now they are detected by the second half of the March C algorithm. So yes, the answer is March C algorithm is able to detect all state coupling faults. So in summary, March C algorithm is able to detect all the coupling faults. So since March C algorithm is already a perfect test, is there anything that we can do to improve it? In 1991, Decoder proposed that actually there is a redundant operation in March C algorithm. So we can simply remove this redundant read 0 to form a new and shorter test. Decoder called it March C minus algorithm. So now the complexity of the March C algorithm is 10n, but it still detects the same 4 models. In summary, in this talk, we introduce a very powerful test algorithm, the March test algorithm. A March test contains several March elements. In each March element, we have operations and the address order. The March tests are very good because they are linear time and the fault coverage are very good. Compared with the traditional test algorithm we introduced in the previous talk, the March algorithms are effective and their test time are linear. And the March C minus algorithm is the shortest algorithm that detects all the 4 faults, and its complexity is only 10n. So the March tests are very useful in production tests nowadays. Finally, before we end this talk, I have a question for you. For a 16 gigabit memory, it still takes 28 minutes to finish the March C minus algorithm, which is still too long. Do you have any better idea to reduce the test time? Please think about it. Thank you for watching the video.